হ্যালো অপূর্ব, কেমন আছো? মিউট, মিউট শুনতে পাচ্ছি না। মিউট, মিউট করা আছে।
হ্যাঁ, হ্যাঁ। হ্যাঁ, সুপর্ণাদি
হ্যাঁ,
ভালো আছি। তুমি ভালো আছো?
হ্যাঁ, হ্যাঁ।
ও,
কেমন ভালো চলছে সব?
হ্যাঁ, এই চলছে। এই খড়গপুরে জয়েন করেছি রিসেন্ট।
হ্যাঁ, সেটা তো শুনলাম। কংগ্রাচুলেশনস।
হ্যাঁ, হ্যাঁ। আমার খুব ইচ্ছে ছিল ক্যালকাটা ইউনিভার্সিটিতে সামনে এসে টক দেবো। তো
হ্যাঁ, সত্যি সেটা হলে খুব ভালো হতো। কিন্তু
হ্যাঁ, হ্যাঁ,
এবারও ভার্চুয়াল কিছু করার নেই। হ্যাঁ, ঠিক আছে। এই তো আস্তে আস্তে সব নন ভার্চুয়াল হয়ে যাচ্ছে। তখন একবার টক দেবে আবার।
হ্যাঁ, হ্যাঁ, হ্যাঁ। আমি আগে একবার এসেছিলাম, তুমি বোধহয় তখন ছিলে বোধহয়, কিন্তু
ওগুলো শুনতে পাচ্ছিস?
হ্যাঁ,
হ্যাঁ,
হ্যাঁ, শুনতে পাচ্ছি।
হ্যাঁ।
হ্যাঁ, প্রদীপ শুনতে পাচ্ছি।
হ্যালো, ওগুলো শুনতে পাচ্ছিস?
হ্যাঁ, 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 আমি শুনতে পাচ্ছি তোকে।
শোনা যাচ্ছে?
হ্যাঁ, হ্যাঁ, হ্যাঁ,
হ্যাঁ, একদম ঠিকঠাক শোনা যাচ্ছে।
ভয়েস তো কমে গেছে দেখছি।
ভয়েস কমে গেছে? না, একদম ঠিকঠাক শোনা যাচ্ছে কিন্তু।
শোভনাদি শোনা যাচ্ছে?
হ্যাঁ, হ্যাঁ,
ভালো
শুনতে
মতো
পাচ্ছি।
শোনা যাচ্ছে, মানে কোনো কম টম নয়। স্পিকারটাকে একটু নিচের স্পিকারটাতে দেখো গ্রিন লাইটটা জ্বলছে কিনা। নিচের স্পিকারটা, বড় স্পিকারটা যেটা আছে না,
এখানে তো ফুল করে দিয়েছি এই সিস্টেম
চলে আসছে।
হ্যাঁ ওইটা লাল আলো জ্বলছে বোধ হয়। ওইটা একটা
কিন্তু আমরা এদিকে
এইদিকে কিছু একটা
সুপর্ণাদি তুমি কি বাড়িতে আছো নাকি?
হ্যাঁ, আমার ওই একটা পায়ে একটু অসুবিধা হয়েছে আজকে, মানে সেজন্য একটু পরে যাব আর কি। হ্যাঁ,
আচ্ছা, আচ্ছা।
হ্যাঁ, শোভনাদি শুনতে পাচ্ছ? একবার বলো কথা।
হ্যাঁ শুনতে পাচ্ছি। হ্যাঁ,
ঠিক আছে, ঠিক আছে না?
হ্যাঁ।
ভলিউম তো কমে গেছে। So, good morning, everyone. So, welcome day 2 of our Rama 2022. So, for the technical session 1, we have the invited speaker, Dr. Apurva Das. And for this session, I request Professor Abhishek Odhikari, Professor of Presidency University, Department of Mathematics, to chair this session. Before that, I request Supunadi to say something about Abhishek.
Okay, it is my pleasure to introduce Professor Abhishek Odhikari. He is currently the head of the Department of Mathematics at Presidency University, but until very recently he was in our department. He was a faculty of Department of Pure Mathematics at University of Calcutta, and we still very much consider him a part of our department. When he's a leading researcher in cryptography, and he's a great teacher and great motivator of students. So, Abhishek da, if you could chair this session, please.
Thank you, Suparna. It's my great pleasure to be here again, and I feel still part of this my institute itself. So it's my great honor to introduce a very young, energetic, nice good teacher, Dr. Apurva Das. So Apurvo, Dr. Das completed his PhD from Indian Statistical Institute, another from a great professor under the supervision of Professor Gautam Mukherjee. After his PhD, he was a postdoc fellow at IIT Kanpur, as well as visiting scientist at ISI Kolkata. And currently, he is an assistant professor at the Department of Mathematics, Kharagpur, IIT Kharagpur, and he has more than 29 international publications with international review. So, without any further delay, let me welcome Dr. Apurvo Das. So now, stage is yours. Thank you.
Yeah, thank you, sir, for the introduction. So it is my great pleasure to being a part of this big conference. So I would like to thank all the organizers for this invitation. So I am really pleased to that. Okay, so shall I share my screen?
Yes, please.
Can you see the screen?
Yes.
Okay. Thank you. So in this talk, I will mainly consider a new operator on associative algebra, which is perhaps new to many of you. This operator is called Rota-Buster operator. So our aim would be to study this operator from algebraic points of view. So let us move. Okay, so introduction or overview. So Rota-Buster operator is an algebraic abstraction of the integral operator. So all of you know what is integration operator or integral operator. So Rota-Buster operator is the algebraic abstraction of that operator. So at first we will study some basic definitions and properties of this Rota-Buster operator. Then we will consider some groups associated to Rota-Buster operator. So these groups are invariant for the Rota-Buster operator, and as an application of this group, we will study deformation theory of this Rota-Buster operator, and in the next, we will also consider some generalizations of Rota-Buster operator in the homotopy context. These operators are called homotopy Rota-Buster operator, and finally, we will give more generalizations of Rota-Buster operator. So this is our tentative plan. So the first contents are divided into 4 parts. So in the first part, we will study Rota-Buster operator and its properties. In the second part, we will consider cohomology theory and deformation theory for Rota-Buster operator. And in the next part, we will introduce homotopy Rota-Buster operator. And finally, we will give some generalizations of Rota-Buster operator. So these are the plan. So what is a Rota-Buster operator, first of all? So as I say, these operators may be new to many of you, but this is not that much new in the sense that will be clear now. So first, we start with the derivation of an algebra. So what is a derivation? So if we start with an algebra capital A, so a derivation we all know is a linear map D from A to A, which satisfies this Leibniz rule. D of AP equals to A into DB plus dA into B. So this satisfies this Leibniz rule, then it is called a derivation. So all of you know that our standard derivative operator ddx satisfies this kind of property. So derivative of two functions f into g satisfies this kind of Leibniz rule. So derivation is a generalization of standard derivative. That means, and the first example of this derivation comes from the polynomial algebra, the standard one. So if a equals to kx, the polynomial algebra, then we define a map d small t from a to a by this formula d of x to the power n is the standard derivative equal to n into x to the power n minus 1. So one can easily check that d is a derivation. Right. So this is the generalization of the standard derivative. Now the natural question that comes in our mind, then what is the integral operator? Or the integral operator satisfies which identity? So the derivation operator satisfies this derivation identity. Now the question is, what is the does the integral operator I of x to the power n equals to x to the power n plus 1 by n plus 1, the integral operator satisfies some kind of identity or not? So one can easily verify that the integral operator satisfies this identity. I of x to the power m into I of x to the power n equals to I common I of x to the power m into x to the power n plus x to the power m into I of x to the power n. So this follows just by direct calculation or by integration by parts formula. One can directly see that. So this is the Rota-Buxter identity. If we replace the algebra kx by arbitrary algebra, then this identity is called the Rota-Buxter identity. And this is the motivation to define the Rota-Buxter operator as follows. So let capital A be an associative algebra. A Rota-Buxter operator is a linear map R from A to A that satisfies the previous identity, that is R of A into RB equals to R common RA into B plus A into RB. Right. So the standard integration operator I of x to the power n equals to x to the power n plus 1 by n plus 1 in the polynomial algebra is a Rota-Buxter operator. Right. So this can be generalized in continuous setup. So if you consider A to be the algebra of continuous functions on the interval 0, 1, which is obviously an algebra under the pointwise product. So we can define a map R, capital R, from A to A. If you take any function f from A, that is the continuous function. So Rf to be a continuous function whose value at the point capital X, small x, is given by this integration formula 0 to x ft dt. So one can easily verify that this operator Rf R is a Rota-Buxter operator. Note that on the right hand side we have a function, this function. So this function is continuous. The function Rf is continuous. In fact, this function is differentiable. We all know from our basic calculus theory that this function is in fact differentiable, hence continuous. So one can easily check that the operator R is a Rota-Buxter operator, and this again follows by the standard integration by parts formula. So another example, if you take A to be the matrix algebra M and K, where the coefficients come from K and P be a square zero matrix, then the operator R from capital A to capital A, which is defined by Rx equal to Pxp. One can easily check that the operator R is a Rota-Buxter operator of the matrix algebra A or M and K. Right. So these are the first or basic examples of Rota-Buxter operator. So let us give some characterization of Rota-Buxter operator. So if you start with an algebra A, capital A, then the vector space, the direct sum vector space A plus A or A direct sum A carries a new associative structure we all know, which is the semi-direct product algebra. This product is given by this formula, So if you take an element A comma A dash and B comma B dash, the two elements from this direct sum, then their product is defined by this formula A comma A dash into B comma B dash equals to AB comma A B dash plus A dash B. Note that in the first factor A comma AB, we use the product of algebra A. Similarly, on the right hand side, we use the product of the algebra A. So therefore, if we have an algebra, then the direct sum A plus A carries a new associative algebra structure, which is called the semi-direct product. With this notation, a linear map R from A to A is a Rota-Buxter operator if and only if, just a minute. Okay, sorry. So a linear map R from A to A is a Rota-Buxter operator if and only if its graph, which is defined by the RA comma A, the graph of the map R, which is the standard notation, is a subalgebra of the semi-direct product. See? So therefore, a map is a Rota-Buxton operator if you know the graph is a subalgebra of this semi-direct product. Okay. So we give the definition of Rota-Buxton operator and give some examples. But what is the initial study of Rota-Buxton operators? So the history of Rota-Buxton operator is as follows. So the Rota-Buxton operator actually first appeared in some combinatorics combinatorics problem in the work of Glenn Baxter and Gian Carlos Rota around 1960s. So they basically consider some generalizations of Rota-Buxton operator, which are now called Rota-Buxton operators with weight. So in last few years, several studies has been done for Rota-Buxton operator. For instance, the Rota-Buxton operator, the free construction of Rota-Buxton operator. So whenever we have some algebraic structure or algebraic object, the free object is important to find out the free object, whether such kind of structure really exists or not. So these are given by free structures. So free Rota-Buxton operators are given in 1972 in the work of Pierre Cartier, famous work of Pierre Cartier for commutative associative algebras. And later, this work has been generalized by Lee Guo and William Keiger in year 2000. So free Rota-Buxton operators are done by these mathematicians. And later, many mathematicians work on Rota-Buxton operators as they are related with many subjects of mathematics. For instance, they are related with combinatorics as the work of Rota did. Similarly, it is related to some operator theory problems as Rota-Buxton operator is an algebraic abstraction of the integral operator, and it is itself interesting from algebraic points of view as well. So in the second reference, that is splitting of operations, these mathematicians, Chengming Bai, Olivier Bélier, Li Guo, and Jiang Ni observed that Rota-Buxton operator can split the algebraic structure. That means if we have a algebra and a Rota-Buxton operator on it, one can produce two bilinear operations on the vector space, new bilinear operations on the vector space. These two operations are in general not associative, but their sum is associative in the sense that they split the associative structure. That means the two operations are neither of them are associative, but their sum is associative. So they observe that Rota-Buxton operator is useful to study splitting of operations. And later, not later, just Marcelo Acuyar also observed that Rota-Buxton operators are useful to study many algebraic structures which are previously known. For instance, associative bialgebra. The famous theory of Greenfield studied bialgebra theory, but Rota-Buxton operators are also related with bialgebra theory and Venn-deform algebras and tree algebras. These are algebraic structures that often appear in the mathematical study of cohomology theory or deformation theory or many related theories. So these kind of structures are appeared there. So Marcelo Aguirre observed that Rota-Buxton operators are related to these algebraic structures. Okay, so next we will recall what is an associative R matrix and its relation with Rota-Buxton operator. So associative R matrix is a very classical object in mathematical physics. Basically, this appear in the study of integrable system or Lie bialgebra theory associated to a Lie algebra. So R matrix can often be considered as an Lie algebra analog or algebraic analog of Poisson manifold that comes from differential geometry. So R matrix, which is also called classical Yang-Buxton solution, is an important object in mathematical physics. They appear in integrable systems. They appear in the classical Greenfield-Lie bialgebra theory and many other related algebraic structures. So the geometric formulation of R matrix is also known as Poisson geometry, which is itself a big subject of research. So this R matrix or classical Yang-Baxter solution is a Lie algebraic version of Poisson structure. So the question is that is there any associative version of R matrix? So this was discovered by Marcelo Aguirre in around year 2000. So the definition is as follows. So suppose we consider an element R, bullet R. So suppose R1 tensor R2, which is an element of A tensor A. So for any element R of this kind, we consider three elements of A tensor A tensor A. The first element is we call R12, which is given by this summation R1 tensor R2 tensor 1. So note that in R12 we put the components of R in first and second component. Similarly, we define R13 where we put the components of R in the first and third factor. Similarly, we define R23, which is an element of A tensor A, and we put the components of R in second and third factor. So these three elements are from A tensor A. Now A is an associative algebra. Therefore, this triple tensor A tensor A is also an associative algebra by component-wise multiplication. Right. So the products of these three elements make sense. Right, because we have the product in A tensor A. An element, so the definition of associative R matrix is as follows. An element bullet R belongs to A tensor A is said to be an associative R matrix if this identity holds. So R13 into R12 minus R12 into R23 plus R23 into R13 equals to 0. Note that R13 is an element of A tensor A. Similarly, R12 is an element of A tensor A, and we use the product of A tensor A here. Similarly for other terms. So associative R matrix. One can easily show that if you consider A to be the matrix algebra MNK and capital P be any matrix, square zero matrix of the MNA, then the element P tensor P. P is an element of the matrix algebra and P is an element of matrix algebra. Therefore, their tensor is an element of MNA into MNK. So this tensor is an associative R matrix. Okay, so these theorems are proved by Marcelo Aguirre. So if R, which is of the form summation R1 tensor R2, is an associative R matrix, so therefore this element bullet R is an element of A tensor A. Therefore R1 comes from A and R2 also comes from A. Is an associative R matrix, then we can define an operator capital R from A to A by this formula. R evaluated at A is summation R1 into A into R2. So note that in between we use the product of the algebra A. So it's a Rota-Buxter operator. So this can be easily followed just if you break this identity in terms of its component and use the definition of this operator capital R, one can easily show that the map capital R satisfies the Rota-Buxter identity, and hence it is a Rota-Buxter operator. But in the particular case of matrix algebra, this is quite interesting that any R matrix gives rise to a Rota-Buxter operator, the first theorem says, And the second theorem says that any Rota-Buster operator on the matrix algebra actually comes from associative R matrix in this way. So if A is the matrix algebra, then there is a bijection, the set of R matrices to the set of Rota-Buster operators. Right. And the one-sided map is given by the first theorem. Okay. As I said, that Rota-Buster operators often split the algebraic structure in the sense that if you have a Rota-Buster operator on an algebra, it will give rise to two products on the underlying vector space capital A. Neither of them are associative, but their sum is associative. So it will be clear in the following definition. So more precisely, a Rota-Buster operator, we will show that a Rota-Buster operator gives rise to a dendriform algebra, which is a kind of a splitting of associative algebra structure. So a dendriform algebra that was introduced by Jean-Louis Lode in the year 2000 in his famous work on Leibniz algebra. So a dendriform algebra is a vector space capital D with two bilinear operations. Two bilinear operations which is denoted by these two notations, preceded and succeeded bilinear operation D tensor D to D, satisfying this kind of identity. Note that we have two operations and the identities are three. So it follows from these identities that neither of these two operations are associative, because in both of the identities, two operations are involved. Both the operations are involved. So therefore, neither of these operations are associative. But if you sum up the left-hand side of the identities, left-hand side of all these identities, you will see that you obtain A star B star C. That is, and on the if you sum up the right-hand side of all these identities, you will get A star B star C, where star is given by this formula, the sum of these two operations. So therefore, if you sum up these three identities, we will get the associativity of the new operation, this sum operation. So if you sum up the left-hand side of these identities, you will get the one side of the associativity, and if you sum up the right-hand side of this identity, we will get the another part of the associativity. So therefore, the sum of these two operations is associative, but neither of these two operations are. So as I mentioned, dendriform algebras were introduced by Jean-Louis Lode in the study of Leibniz algebras, and they have many connections with Rota-Buster operators in the study of planar binary trees and many aspects of combinatory and shuffle algebras and many other things. So we will be interested in the Rota-Buster operators with dendriform algebra. Okay, so let me give one example of dendriform algebra. So if you consider D to be the polynomial ring, so we will not consider its usual product. So we'll consider D equals to Kx, and we define two multiplication xm into xn. The first multiplication is given by this formula, x to the power m plus n plus 1 by n plus n, and the second operation is given by x to the power m plus n plus 1 by m plus 1. So these two operations, one can easily check that these two operations satisfy the dendriform identities, three identities of the dendriform algebra. So another interesting example that was given by Jean-Louis Lode that comes from planar binary trees. Okay, so actually this planar binary tree is a combinatorial object that is quite related to dendriform algebra. In fact, the free dendriform algebra comes from planar binary tree. So the next theorem says that a Rota-Buster operator gives rise to a dendriform algebra. Okay, so let capital R from A to A be a Rota-Buster operator. So we have Rota-Buster identity. Then the vector space capital A carries a dendriform algebra structure. So dendriform algebra structure means it should have two products. The first product is given by this operation A into RB, and the second operation is given by A succeeded B equals to RA into B. Note that here we use the product of the algebra A because A is an algebra. Similarly, here we use the product of the algebra A. So, if we have a Rota-Buxter operator, then the underlying vector space carries a dendriform algebra structure. And we know that the sum of these two dendriform operations is a new associative algebra structure. So, therefore, if we sum up these two operations, we get a new associative algebra structure on the vector space capital A. And the operation A, which we denote by star of R, B, equals to the sum of these two operations. ARB plus RAB, right? So this is a new associative algebra, not the initial one or given one. So this associative algebra structure will be used in the construction of the cohomology theory for Rota-Buxter operator. That is why I mentioned here. So this associative algebra structure. Okay. So next we move to cohomology and deformation theory for Rota-Buxter operator, or cohomology or deformation theory for integral operator in particular. So what is a cohomology theory? Okay. So cohomology is a invariant of the algebraic structure. For instance, if we have any mathematical structure, given a mathematical structure, we often associate some invariance to it. For instance, if we have a set, we use the cardinality of the set, which is an invariant of the set theory. For instance, if two sets are bijective, then they should have the same cardinality. Similarly, for vector space, we have dimension. Two vector spaces are linearly isomorphic if and only if they have the same dimension. Similarly, for rings and algebra theory, we have some invariants. They are cohomology theory, or maybe homology theory, or maybe some others. So, cohomology theory is an invariant for algebra. So, cohomology is a very rich research topic that was discovered around 1950 in the famous work of Gerhard Hochschild for associative algebra. In the first paper, Hochschild introduced the cohomology theory for associative algebra and cohomology theory of groups also. So later, cohomology theory has been discovered for many algebraic structures. For instance, Lie algebras or many others, Leibniz algebras, Poisson algebras, and many other algebraic structures. Cohomology theory has been developed, and such a structure becomes more important when in 1963 Haber studied the deformation theory for associative algebra. See the third reference. In this paper, Haber studied the deformation theory. Fourth paper. On the fourth paper, Haber studied deformation theory for rings and algebras, and they showed that deformation theory for any rings or any algebras are closely related to the cohomology theory, in the sense that there is a term or there is a line that cohomology theory, deformation theory is governed by the cohomology theory. So all these papers are the classical papers nowadays. All these papers are published in the most reputed journal of mathematics, Annals of Mathematics mainly. So, and subsequently, cohomology theory for various other algebraic structures are also done. Okay. So our aim here is to introduce a cohomology theory for Rota-Buxter operator. Note that Rota-Buxter operator is not an algebra, but an algebraic structure. So it is an operator. So it can be considered as an algebraic structure. So we will study cohomology theory for this Rotabuster operator. That is, given a Rotabuster operator R, we will associate some groups which are invariant in some sense. So let capital R from A to A be a Rotabuster operator. So we define for each n greater than 0 a group Cn R A comma A is the Hom space. So the space of all n-ary multilinear maps from A to A, Hom of A to the power n comma A. And we define a map delta nr from the nth space to n plus 1 space. So note that take an element f here, f from CNR. So delta n f should be an element of Cn plus 1, right? So it is a n plus 1 ary multilinear map. So it will be acted on n plus 1 elements, a1 dot 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 a n plus 1, and the image should be an element of capital A, and the definition is given by this formula. So R is a Rotabuster operator, so R of A1 is an element of the algebra A, and F is an element of Cn. Therefore, this element F of that thing is an element of A, and we take the product in between. Similarly, for the second term, we have R of A1 is an element of the algebra A, and F of that thing is an element of the algebra A. We take the product here. So this entire thing is an element of the algebra A, and now we apply R. Similarly, for other terms, they are also belongs to the space A. So the map delta nr makes sense. So our main theorem is, if you apply consecutive 2 delta n's, then this map is 0. So delta nr composition delta n minus 1 r equals to 0. More precisely, we obtain a quotient complex of this kind. C0r, we apply delta 0r to C1, and similarly, if we apply this thing at the nth level, we get CNR, and we apply delta nr to get Cn plus 1 r a comma a, and so on. Since from the previous theorem, since the composition of two consecutive maps is 0, that is, if we apply first this map delta n minus 1 and then again delta, the composition is 0 map, which says that image of the first map, image of delta n minus 1 should lie inside the kernel of the next map, kernel of delta n plus 1 by r. Since the consecutive two maps, composition of consecutive two maps is 0. And therefore, from this inclusion, we can take the quotients of these two things. So we define HNR of A comma A is the quotient of that thing, kernel of delta n r by image of delta n minus 1 r. And this is makes sense for all n greater than 0 at each stage n. This makes sense. Note that kernel of this thing is a subspace of CNR, and CNR is just a Hom space, so it is a group under the addition of two multilinear maps. So this is a subspace of this group. So therefore, this is a group. And similarly, this also has a group structure. We take the quotient of these two groups. These groups are in fact abelian group, since we are taking the addition of multilinear maps. So therefore, their quotient is an abelian group, and these groups are called the cohomology groups of the Rotabuster operator. Right. So what was our strategy? So if R is a Rotabuster operator, we consider the innate quotient group or Cn as the Hom space, Hom of A to the power n comma a, and we define some maps delta nr some suitable way so that their composition consecutive to map when we apply it becomes 0, and therefore we get image of delta n minus 1 is a subspace of kernel of that thing, and if you take the quotient you get the cohomology of the Rota-Buxton operator. Now we move to deformation theory of Rota-Buxton operator. So in a deformation theory of some algebraic structure or some geometric structure, it means, as the name suggests, deformation. By deformation, we always mean that we are allowing to perturb the structure. So here we also do the same thing. So if we have an associative algebra, let capital A be an associative algebra, and capital R from A to A be a Rota-Buxton operator. So we want to deform the structure capital R. So for that we consider the space AT, A of capital small t inside the double bracket. That means the spaces, the elements of this space A of t is given by a formal power series with coefficients from A, with and the variable is t. So the elements of this AT space is formal power series in T with coefficients from the algebra A. So elements are of this kind: summation I greater than equals to 0, t to the power I, t is a parameter, and the coefficient of t to the power I is AI, where AI comes from the algebra A. So this formal space AT carries an associative algebra structure induced from the associative algebra structure on A, and the associative product on AT is given by this formula. If you take this element, one element, and another element, summation j greater than equals to 0, t to the power j bj, then their product is defined by this formula. Summation I comma j greater than equals to 0, t to the power I plus j ai into bj. One can easily check that. So note that here we use the product of the algebra ai bj in between ai and bj. Since A is an associative algebra, one can easily check that this product is also associative. So AT becomes an associative algebra. Note that this space is formal space as its elements are formal power series. So we don't bother about convergence issues. So we have only formal elements here. So what is the formal deformation of the Rota-Buxton operator R? So a formal deformation of R is given by a formal sum of this kind. So RT equals to R plus T R1 plus T square R2 plus dot 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 so on, where each of Ri is a homomorphism from A to A or linear map from A to A. So since it is a deformation, so the deformed object should be a Rota-Buxton operator. Since we are deforming a Rota-Buxton operator, so the deformed object, so RT should be a Rota-Buxton operator, and this is what we expect. So we assume that the RT should be a Rota-Buxton operator, and it is a deformation of R, means that if you write the formal expression RT, so the constant coefficient must be R. So we are deforming the map R. So therefore, a formal deformation of R is just a formal power series where each Ri belongs to hom of A comma A, such that RT is a Rota-Buxton operator. Note that this makes sense. RT from AT to AT is a Rota-Buxton operator makes sense because AT is an associative algebra. Just to see the previous first part of this slide. So it is an associative algebra, and we expect that RT is a Rota-Buxton operator. Right. So a formal deformation is given. Now there is a notion of equivalence of two formal deformations. So suppose RT is a formal deformation and RT dash is another formal deformation. What is the meaning of this equivalence of these two deformations? There is a notion which I am not going to details because it is a bit technical. So we just state something. Two such deformations, RT and RT dash, are equivalent if there is some suitable algebra map. This suitable means bit technical, so I'm not going into that. So suitable algebra map phi t from 80 to 80. Note that 80 is an associative algebra, and we consider phi t to be an algebra map which satisfies this property. So in that sense, phi t is an associative algebra map which commutes with the Rota-Buxton operators RT and RT dash. Right. So in the deformation theory, we are mostly interested in two kinds of questions. Namely, if we have an algebraic structure, the first question is that when the structure is rigid, that means you cannot deform that structure. And the second question is that parameterize or gives some simple description of the equivalence classes of all deformations. This is for the deformation space. This kind of questions we face. So similarly, for Rota-Buxton operator, we can answer this kind of question. So for that, we first define this notion. A Rota-Buxton operator R is said to be rigid. So rigid means it has no deformation. So it is kind of rigid thing. So it has no deformation. In the deformation language, it means capital R is said to be rigid if any formal deformation is equivalent to the undeformed one. By undeformed one, RT dash means RT dash equals to simply R. So it has no formal terms. The coefficients of T dash, T squared, and higher terms of T are vanished. See? A formal deformation of R is a formal sum of this kind, which is a Rota-Buxton operator. Note that if R1, the first coefficients of T square are all vanished, then RT equals to R is a deformation, obviously a deformation. So Rota-Buxton operator R is said to be rigid if any deformation is equivalent to the undeformed one. So RT dash equals to R. So the question is that when a Rota-Buxton operator is rigid, right? So we find the answer. So we show that if the first cohomology group of the Rota-Buxton operator vanished, then the Rota-Buxton operator R is rigid. Right. So therefore, we find a sufficient condition for the rigidity of a Rota-Buxton operator in terms of the cohomology theory. So if the first cohomology group is vanished, then the Rota-Buxton operator R is rigid. So similarly, one can also ask the set of all equivalence classes of deformations of R. Can we parameterize this space by some simple space? So this question is usually very difficult, but if we consider some simple kind of formal deformations, which are called infinitesimal deformations, we can parameterize them. So what is an infinitesimal deformation? An infinitesimal deformation of capital R is a formal deformation over the base ring kt by t square. That means a formal deformation, an infinitesimal deformation is a formal deformation of some special kind over the base ring kt by t square. That means, so from t square onward, the higher powers are vanished. That means an infinitesimal deformation should be of the form RT equals to R plus T R1. So from t square onward, the terms are not there in the case of infinitesimal deformation. Right. So infinitesimal deformation. Similarly, one can define the equivalence between infinitesimal deformations. So we show that there is a bijection between the set of infinitesimal deformations of R modulo that equivalence relation. That means equivalence classes of infinitesimal deformation. The left hand side is equivalence classes of infinitesimal deformation, and the first cohomology group of the Rota-Buxton operator. Therefore, this theorem says that the space of equivalence classes of infinitesimal deformation are parameterized by the first cohomology group. Yeah. Okay, so another kind of deformation one may consider. So these are finite order deformation. Finite order deformation is a generalization of infinitesimal deformation. In the case of infinitesimal deformation, we consider that it is a formal deformation over the base ring kt by t square. So a finite order deformation is a formal deformation over the base ring kt by t to the power n plus 1. So when capital N is 1, we get infinitesimal deformation. So therefore, in a formal deformation, in a order n deformation, so the order n deformation should be look like this fellow. Rt to the power capital N, which is of the following form: R plus T R1 plus T to the power capital N into Rn of this form. Now the question is that suppose we have a formal deformation, order n deformation of this kind. So when can we extend it to a deformation of next order? So that means, see the next definition, an order n deformation Rtn is extensible if there exists a map Rn plus 1. So we require a map Rn plus 1 belongs to Hom of A, F such that the new thing Rtn plus 1. So this is the first up to t to the power n is Rtn plus this new thing. If we add this thing to Rtn, this becomes a deformation of order n plus 1. So this kind of extension is not always possible, because in this definition we are asking for the existence of this kind of Rn plus 1. So this kind of extension is not always possible. We show that if the second cohomology group of the Rota-Buxton operator vanish, then any order n deformation can be extended to a deformation of next order. So this is another main theorem. So if the second cohomology group vanish, then any order n deformation is extensible. So now suppose you start with a infinitesimal deformation, which is a order 1 deformation, as I said. So if the second cohomology group vanish, then order 1 deformation can be extended to order 2 deformation. Similarly, if the second cohomology group vanish, so second cohomology order 2 deformation can be extended to order 3 deformation, and so on. So if the second cohomology group vanish, so therefore any infinitesimal deformation or any finite order deformation can be extended to next order, next order, next order, and so on. So what is order infinity deformation? Think about n equals to infinity. What is order infinity deformation? So it has no bound. That means it is a formal power series. So in other words, an order infinity deformation is nothing but the formal deformation that I given at the beginning. So this one, formal deformation. Therefore, if the second cohomology group vanishes, then any infinitesimal deformation or any finite order deformation can be extended to a deformation of infinite order. That is, can be extended to formal deformation. Right. Okay. Next, we will introduce homotopy Rota-Buxton operator. So in the Rota-Buxton operator, a Rota-Buxton operator is defined on an algebra, right? On an associative algebra. A homotopy Rota-Buxton operator is not defined on an algebra, but in homotopy algebra. So in homotopy algebra, so the operations are not usually associative, but it holds up to homotopy in the sense, in the following sense. So an A infinity algebra is a graded vector space, script A of this kind, together with some collection of maps mu1, mu2, dot dot, where mu1 is a linear map of degree -1, mu2 is a bilinear map of degree 0 and so on. The mu k, the kth map, which is a k-array operation of degree k minus 2. And these all maps, infinitely collection of maps, satisfying some identity. So in fact, for each n greater than 1, we have one single identity. So these kind of identities are there. So infinity algebras were introduced by Jim Stashev in the study of loop spaces in the topological theory. So this is the algebraic counterpart of his notion, infinity space. So any associative algebra, graded associative algebras, differential graded associative algebras are particular cases of infinity algebra, because if the underlying graded vector space here is concentrated only in degree 0, we get associative algebra. You will see that all other operations are 0 unless mu2, and mu2 is associative from this identity. So infinity algebra is more general than all associative algebras, graded associative algebras, and differential graded associative algebras. So we move to the third example here. So given a topological space, pointed topological space, that is when x is a topological space and x naught is a base point, that is a fixed point of the topological space, let omega x be the space of all loops based at x naught. So omega x is the set of all continuous maps from 0, 1 closed interval to x, whose first point, the initial point and terminal point at same x naught. So one can show that this space carries a concatenation product, that is concatenation of two paths, and this concatenation product is not in general associative. But when you take the homotopy classes of that paths, it becomes a group structure, actually known as fundamental group of the topological space. And since it is a group structure, the homotopy, when you take the homotopy class, it becomes associative. But before taking the homotopy class, the concatenation of paths is not associative. So this product is actually homotopy associative, and therefore K of omega x is an infinity algebra. So infinity algebra appears in many places in mathematical physics. So in the context of infinity algebras, we can also consider the direct sum. So if capital A, script A, mu1, mu2 is an infinity algebra, then their direct sum A also carries an infinity algebra structure with this kind of product, where k is greater than 1. Since it is an infinity algebra structure, we have to define for each k, there is a k-array operation, and this k-array operation is given by this kind of formula. So we define homotopy Rota-Buster operator or strict homotopy Rota-Buster operator on an infinity algebra. So let script A be an infinity algebra. A homotopy Rota-Buster operator is a degree 0 linear map script R satisfying this kind of operation. So note that A has k-array operations mu k for each k. So the operator R should be compatible with all mu k's. And for each k, we have this identity. So note that for k equals to 2, this identity is same as our Rota-Buster identity. So similarly, we have characterization of homotopy Rota-Buster operators. So a degree 0 map script R from script A to script A, where script A is an infinite algebra, is a strict homotopy Rota-Buster operator if and only if the graph of this map, script R map, is a infinity subalgebra of this semi-direct product. So this generalizes the result from non-homotopy case. So a map is a Rota-Buster operator if and only if its graph is a subalgebra. And similarly, we proved here in the homotopy context. So some examples of homotopy Rota-Buster operators are given in my paper. So any Rota-Buster operator is obviously a homotopy Rota-Buster operator. Similarly, we can show that if we start with an algebra with a Rota-Buster operator R, then its quotient complex. So an algebra A associated to a Hochschild complex. So its quotient complex carries an homotopy Rota-Buster operator. Now in the non-homotopy case, we have seen that an R matrix gives rise to a Rota-Buster operator. So it is expected that there should be a notion of R infinity matrix or homotopy R matrix which will give rise to homotopy Rota-Baxter operator. So this is not yet discovered. So we are looking forward to them. So we are looking for the notion of R infinity matrix and try to produce homotopy Rota-Baxter operator. Okay. So in the non-homotopic case, we have studied deformation theory of Rota-Baxter operators. So the question is that can we study deformation theory for homotopy Rota-Baxter operators or homotopy algebras, or in particular infinity algebras or homotopy Rota-Baxter operators or this kind of homotopy structures? So deformation theory for infinity algebras or homotopy algebras are already well studied by many mathematicians, famous mathematicians. So for instance, see the references by Alice Filowsky and Michel Penkava, deformation theory of infinity algebra. So by following this approach, their approach, one can also study deformation theory of homotopy Rota-Baxter operators. So next we just give some generalization for your interest of Rota-Baxter operators. So note that in the Rota-Baxter identity, one can easily see that the identity map is not a Rota-Baxter operator. Identity map of the algebra. So to make the identity map is a type of Rota-Baxter operator, we may introduce a notion of Rota-Baxter operators of with weight, which was first introduced by Rota in 1969 and further studied by many mathematicians. So a map R from A to A is a Rota-Baxter operator of weight lambda belongs to K if we have the following identity. So RA into RB equals to R of RAB plus A RB plus lambda into AB. So lambda is a scalar. So note that the identity map is a Rota-Baxter operator of weight -1. Similarly, if you consider the space of all real sequences, the space of real sequences forms an algebra with the component-wise multiplication. So if you have a sequence, if you have two sequences, then the nth term of the product sequence is just simply xn into yn. So the space of sequences is an algebra, and from the space of sequences to the same space, we define this operation. So if a1, a2, an is a sequence, we define a new sequence whose first term is a1, second term is a1 plus a2, third term is a1 plus a2 plus a3. That is the sequence of partial sums on the right hand side. So one can easily check that this map is a Rota-Baxter operator of weight 1. So similarly, there is a notion of twisted Rota-Baxter operator. In the case of Rota-Baxter operator, twisted Rota-Baxter operator, we have some map H by which we have to twist the Rota-Baxter identity. So H is a suitable map from A tensor A to A, and H twisted Rota-Baxter operator is simply a map R from A to A which satisfies this kind of identity. RA into RB plus equals to this kind of thing. So note that if H equals to 0, we get the usual Rota-Baxter operator. And in the previous case, when we consider Rota-Baxter operator with weight, if lambda equals to 0, then we get Rota-Baxter operator. So both of these are generalizations of Rota-Baxter operator. So the first question is that can we study cohomology and deformation theory for this kind of operators? So the answer is yes. So I have studied cohomology theory and studied deformation theory for both of these operators. So there are some other generalizations of Rota-Baxter operators. So in the context of Lie algebra, we can also study Rota-Baxter operators. So let G be a Lie algebra. A linear map is said to be Rota-Baxter operators of weight lambda if the following identity holds. So here we have the Lie algebra bracket. Similarly, one can also define Rota-Baxter operators on group. So if G is a group, a set map R from G to G is a Rota-Baxter operator if the map R satisfies this identity. Note that this identity is little bit different than all other identities that we have considered, because in the case of associative algebras or Lie algebras, we have addition of vector spaces. But in the case of group, since group is a set, it has no addition. So therefore, this identity is little bit complicated. One can easily check that the inverse map of a group is a Rota-Baxter operator. So one may ask the following question: can we define cohomology and deformation theory for this kind of Rota-Buster operators? So deformation theory for Rota-Buster operators for Lie algebras are already studied, but the deformation theory of Rota-Buster operators on group is not yet studied because it is done in just last year, this definition. So this has to be explored. Another generalization of Rota-Buster operator is given by matching Rota-Buster operator. So this is just a generalization of the last part of this slide. So let us consider this A to be C01, which is the algebra of all continuous functions on the space 0 to 1, and X subset of A be any subset. Then for any K belongs to X, we can define this integral formula Rk of f evaluated at X. So K belongs to X, so K is also a continuous function. So we can take the integration of K into X, the function. This is just the standard integral operator that we know from integral calculus with kernel kappa t. So this kind of operators satisfy a notion called matching Rota-Buster operator. So what is a matching Rota-Buster operator? So if we start with an algebra capital A and X be any set, so a matching Rota-Buster operator is a collection of maps, linear maps, labeled by the element of the set X, satisfying this kind of identity. So Rx A into Ry of B equals to Rx A Ry B plus Ry Rx A into B. These kinds of elements. So all these generalizations appeared from various motivations that we already know. That, for instance, this example comes from basic sequence theory or basic analysis theory. Similarly, this example comes from just basic integration theory or basic integral calculus. So there may be many operators that are not yet discovered that comes from basic analysis or basic algebra. So this thing has to be discovered. So I will encourage young students to learn this subject. There are many problems here, interesting problems which has to be found. So I add some references. These are the standard references for Rota-Buster operators. And in the end, I will put some of my references. So this talk is based on the first, second, and fourth references. Yeah. Thank you for your attention.
Thank you very much for your nice presentation. I'm sure
Yeah,
that many of the students as well as those who are watching this will have a few questions.
Yes.
I can see in the chat box few interesting questions. First was asked by Nilaho Dotto. Sir, can you please tell if the Rota-Buster operator can be used in from algebra?
Can be used
In tree form algebra. Tree form algebra.
Okay, so I had mentioned that Rota-Buster operator gives us to a dendriform structure.
Okay, so he has already answered
So
it.
I have already given that.
Okay. And the next question is from Uday Shankar Roth. His question is Rota-Buster operator a self-adjoint or unitary operator?
No, we are not considering algebras with involution in the case of like operator theory. So we are not dealing with involutive algebras. So there is no star operation there. So we cannot talk about involutive or self-adjoint thing.
Okay. Then another very quick question is, I think it should be the Rota-Buster operator. I think this collection of Rota-Buster operator are abelian or non-abelian groups.
Okay, so this is an interesting question. Yeah. See, for the Rota-Buster identity.
Okay.
So see for the Rota-Buster identity. Okay, so this identity a Rota-Buster operator is a linear map R satisfying this operation. So you will see that if R is a Rota-Buster operator and capital S is another Rota-Buster operator, you will see that their sum is not a Rota-Buster operator. So the obvious operation should be the sum operation, right? So you will see that their sum is not a Rota-Buster operator. So in general, the set of Rota-Buster operator is not has no multiplication or no addition there. So it is not a group.
Okay. So another question is by Rishi Das. Suppose for some algebra, the inverse operator of Rota-Buster operator defined over that algebra exists, then will that inverse operator also hold the same kind of properties as the differential operator?
Yes, exactly. When a Rota-Buster operator is invertible, then its inverse is a derivation. And similarly, for if a derivation has some inverse, then its inverse is a Rota-Buster operator. So derivation and Rota-Buster operators are kind of inverse of each other. See for this slide, in this example, in the polynomial case, so d of x to the power n equals to n of x to the power n plus 1. This is just the derivation operator, and its inverse operator is integral operator. So this is a derivation operator and this is a Rota-Buster operator. So they are inverses to each other. This is true for in any algebra.
Okay, so I cannot find any further questions over here. So if any,
I have a simple question. Can I ask it?
Yes,
yes,
yes.
please continue.
Yeah. So I think you just mentioned the classical Young-Baxter equation there.
Yes.
So the solution of the classical Young-Baxter equation, you were saying them they are the R matrices, and for the algebra A is MNK. You have found out an one-to-one correspondence between the this theorem set of R matrices and set of Rota-Baxter operators.
Yes, yes.
So what about the Young-Baxter equations, not the classical ones? So is there any relation between these Rota-Baxter operators and the Young-Baxter equations? I mean, the solution of Young-Baxter equations?
Yeah, I understood your question. Yeah, first of all, there is a notion called Rota-Buster operator. Yeah, actually, in the case of classical Young-Baxter equation or the standard R matrix, they are defined on Lie algebras. So in this case, we define for associative algebras, that is why we call the associative R matrix. So in the case of Lie algebras, there is a notion of Rota-Buster operator. So any R matrix obviously gives an Rota-Buster operator on the algebra. But this kind of theorem, I think it is not true or not there.
Because but the every solution of this classical Young-Baxter equation can be generalized to a solution of a Young-Baxter equation. I'm not sure there is a theorem. I think Pavel Ettinger wrote a paper on that. So that means that there should be some correspondence between this Rota-Baxter operator and this solutions of Young-Baxter equation. So I mean, is there any work that is going on?
Yeah, maybe if you start with a classical R matrix or a simply R matrix on the Lie algebra G, then one can associate an associative R matrix on the universal enveloping algebra UG.
Yeah.
And from that, maybe you can correspond something like that.
Yeah,
So
because if you deform it, then it becomes a quantum group, and that means that's a solution of Young-Baxter equation.
Young-Baxter equation, yeah.
Okay, thank you very much.
So is there any other questions from the audience? Okay, if that is not the case, then let's thanks once again our speaker, Dr. Apurva Das. Thank you very much.
Yeah, thank you, sir. Thank you so much.
Yeah, now I hand it over to Nadeem. Yeah, please.
Thank you, Vishika, for chairing this session. Thank you, Apurva, for your nice and informative talk.
Yeah, thank you, Pradeep, and thank you all for the invitation. Yeah.
So, okay, so we'll move in the next lecture. So, for the next lecture, I invite Professor Ashok Kumar Das from our department to chair the session. And the speaker is Dr. Saurabh Pal from IIT Mumbai. Saurabh, are you here?
Yes, indeed.
Okay. So now I request Sunil to say something about IDZ.
It is my great pleasure to introduce Professor Ashok Kumar Das. He is a senior professor in this department. He is an eminent graph theorist. I request Professor Das to kindly chair the session.
Good afternoon. I'm happy to introduce Dr. Saurabh Paul. He is one of the alumni of our department and did his PhD from ISI Bangalore in 2012, and currently he is associate professor at IIT Mumbai. And his research interest includes multivariate operator theory and several complex variables. I invite Dr. Saurabh Paul to present his lecture. And hope all of you.
Thank you very much, Professor Das. At the beginning, I would like to thank the organizers for giving me this opportunity to give a talk. I was a passed out of Calcutta University quite a few years ago, and it's wonderful to give a lecture here. Well, once again, I'd like to thank the organizers, Pradeep and Shuparna, and my old friend Dhananjay. I can see Dhananjay here. So I will use the slides and the board also simultaneously. Okay, I start. So, is it visible? Is the screen visible?
Not yet, not yet.
Is it visible now?
Yeah.
Yes, sir.
Yeah. So the title of my lecture is Dilation and Distinguished Varieties in a Family of Domains Associated with Spectral Interpolation. So to begin with, I'd like to focus on the notations that I am going to use. So first of all, the unit disk in the complex plane, this bold D, it means that open disk with center at origin and radius 1. And D closure is the closure of it. And the unit circle is, we use this notation. Sometimes people use S1 for this. And here we will deal with bounded linear operators acting on complex Hilbert spaces. So I was hearing some operators in the previous lecture, but here we will focus on only bounded linear operators acting on complex Hilbert spaces. And this collection is called B of H, this algebra. A contraction is an operator that has norm less than or equal to 1. This is what is called a contraction in operator theoretic language. And a normal operator is an operator. We are all familiar with this. So it commutes with its adjoint. And a unitary is a special normal operator for which the adjoint being the inverse. Okay. Now, as I was requested by the organizers and Professor Dhananjay in particular, to make this talk accessible to the students. So I'll try. So yeah. So is the board visible here? Is the board visible here? Screen?
Yes,
Yes, yes.
Yeah, thank you. So we are dealing with B of H. So this is here H is a Hilbert space. So this H is a Hilbert space. And this BH is the algebra of all bounded operators on H. So by the word operator, I will mean only bounded operator once again. So this BH is an algebra, and in particular, it's a sister algebra. One can easily show it's a sister algebra. So if we talk about the closed unit ball of this, so we use this notation for closed unit ball with center at 0 and radius 1. So what is that? It consists of all such operators T such that norm of T is less than or equal to 1. Now, if you want to study any operator, any bounded linear operator, it suffices to study this object only. Why is that? Because given any operator, say J in BH, okay? So this J is nothing but a scalar times a contraction. You just divide J by its norm. It will become an operator in the unit ball, the closed unit ball. Okay, and since it is a bounded linear operator, the action of G precisely depends upon, if you multiply it by a scalar, the action does not change. The action of the operator is just a multiple of that scalar and nothing else. So if you want to, if you can get hold of the behavior of a contraction T, okay, then what is alpha times T for a scalar alpha? It's precisely the action of T multiplied by alpha, nothing else. So my point is, it suffices to study only the contractions if we talk about one variable operator theory. Now, what is a contraction? A contraction is an operator with norm less than or equal to 1. It's an abstract object, indeed. Now, the goal of mathematics, as always it has been, to express or to approximate or to realize an unknown object in terms of known objects. So this is the reason quite a few years ago, in 1951, Professor von Neumann is a mathematician who we all know. He introduced the notion of spectral set. I am going to briefly define it for one operator. A compact set is subset of C is called a spectral set. For an operator T belongs to BH. I am not talking about contractions, any operator. If two things happen. Number one, the spectrum of T is a subset of K. And number two is von Neumann's inequality whole. What is von Neumann's inequality? What does it mean? It means given any rational function f, then f of t, its norm, is less than or equal to the supremum norm of f. So this is the notation for supremum norm. So this means for all f. So this is the rational algebra over K. What does it mean? It means f is a rational function that does not have any pole inside K. Okay, so this algebra, this is the algebra of complex valued rational functions having no pole in K. Okay, so if these two conditions hold, then we say that K is our spectral set for T. Now, what is meant by f of T? This is simple. This is simple. If you choose any rational function f of this form, P upon Q, where this P and Q are polynomials. So yeah, they are polynomials, meaning they are in CZ. Then we know what is meant by P of T. So P is a polynomial in one variable. Just put T in place of that variable. That is what is P of T. So if Pz is say 3z square plus 2z plus 5, somewhat like this, then P of T will be simply 3t square plus 2t plus 5 times I, identity operator. So you know what is P of T and what is Q of T. Now since Q does not have any zero inside K, so this Qt is invertible. This inverse will exist. So f of T is actually, then it makes sense this way, P of T times Q of T inverse. This is how it makes sense. So eventually f of T is nothing but another bounded operator and nothing else. So the von Neumann inequality tells us that the norm of this bounded operator f of T is less than or equal to the supremum norm of f over K. Okay, and this holds for any rational function that does not have any pole inside K. So if these two conditions are satisfied, then K is called a spectral set for the given operator T. Now, if you just follow the definition of spectral set, if you choose any superset of K, that is a compact set. If you choose K1 and K1 is compact, and if this K is a spectral set for T, then so is K1. You just look at the two conditions. So this will follow clearly, and this will also follow. So a super compact set of a spectral set is always a spectral set. So our task is to cut it down. How fine can we make by cutting it down? Okay. Now, why is this notion so important? The reason is the following. So again, this is the famous theorem due to von Neumann. An operator is a contraction. An operator on a Hilbert space H is a contraction, meaning it has norm less than or equal to 1. If and only if this closed unit disk is a spectral set. For this operator. So this is what is called characterizing the unit wall of BH by means of the closed unit disk of the complex plane. Just look at an operator is a contraction if and only if B closure is a spectral set. If you follow the definition, one side is very trivial. If decloser is a spectral set. If you put decloser in, if k is equal to decloser, meaning the closed unit disk, okay, and if these two conditions do satisfy, then T is a contraction. Definitely, you put f equal to identity, this function. You put this f equal to the constant function. It does not matter. Or you can put fz equal to z. This is a rational function. And norm of T. Then the left hand side will give you norm of T, and that will be less than or equal to 1 on the right hand side, because K is the unit disk. Okay. So one side is very trivial. If decloser is a compact, if decloser is a spectral set, then T is a contraction. But the other side is non-trivial. Okay. Indeed, this theorem is one of the pillar theorems in operator theory, in one variable operator theory. Why? Because you just look at an operator. It's a contraction, and it's an abstract object given a contraction T, meaning norm is less than or equal to 1. You never know what is T. It's an abstract object, but this object, this decloser, is something that we all know. So this is kind of realizing an unknown object by means of a known object. Okay, so this was the aim of introducing the notion of spectral set for an operator. Now, the next step was how to realize a contraction by means of some known operators. Okay, so what are the best operators in the world? The best operators are normal operators. Why? Because if you have a normal operator, you have spectral theorem for it. In case when n is normal, and if n is acting on a finite dimensional space, then it is a matrix. So what is a normal matrix? A normal matrix is something that is diagonalizable, and vice versa. Okay, a matrix is normal if and only if it is a diagonal matrix. So if you have a diagonal matrix, then it's very easy to deal with. You know its invariant subspaces, you know its eigenspaces, you know everything about it. So one goal of operator theory is how to realize a given operator in terms of a normal operator. So that is something that was given by Bela Nas somewhere inside it, and it is identified with a part of something that lives on the boundary. So a natural question arises: what happens with other compact sets? For example, if you take an annulus, then what happens? Now we can define an annulus, say for example. So what is here? So this is so call this an annulus, where this R lies strictly in between 0 and 1. Now, if you consider the annulus closure, and if we say that if we take an operator for which this annulus closure is a spectral set, so here we have something that is also a familiar domain. So we are removing one disk. So this is your annulus. Now, if we consider an operator T for which this ER closure E is a spectral set. Now the question is, can we find out a normal dilation to the boundary? And its boundary consists of two circles, this one, the outer circle, and the inner circle. The answer is yes. The answer is yes. Once again, one can find out a normal operator N that lives on the boundary of this annulus, and it dilates T. So in geometric language, we say that rational dilation, this is what is called rational dilation. See, this F is a rational function. So this phenomenon is called rational dilation. So the rational dilation succeeds on the unit disk of the complex plane, and it succeeds on an annulus because given any operator T that has annulus closure as a spectral set can be dilated normally to its boundary. So the next step was the next question was whether or not it holds on a multiply connected domain. So an annulus is something that you have a solid disk and then you remove another disk from it. So it's a disk with one hole. Now, if you have a disk with more than one hole, if you have a disk with, say, more than one hole, if you have this to be your domain, then the question is whether you can find out, given any operator T for which, if you call it, say, BR, then given an operator T for which this BR closure as a spectral set, whether or not it can be dilated to its boundary. The answer is no. The answer is no. So this annulus was the success of rational dilation on annulus was a famous paper by G. Maglard in Annals of Math. And this answer is no for a triply connected domain or a multiply connected domain. That was also one of the top papers of operator theory that appeared in Journal of American Mathematical Society. And it was due to Makla and Richel. So since then, it has been a great interest what happens with other domains, not only in C but also in Cn. If we move from one to several variable, the notion of spectral set remains the same. Only the spectrum will be replaced by something called joint spectrum because we are dealing with multivariable operators, and the other things will remain same. So now I go back to my slides and let us define what is a spectral set in several variable, and what is distinguished boundary. The notion of boundary will be replaced by distinguished boundary. What is a distinguished boundary? For example, if you deal with the boy disk D2, its topological boundary is not the 2 torus. The 2 torus is something that is much thinner than the topological boundary. Its topological boundary is union. So this is what is the topological boundary. Okay, and this 2 torus is something that is called the distinguished boundary. Now let us define it formally. So you just look at the screen. Is it readable?
Yes.
So if you have a couple of commuting n couple of operators acting on a Hilbert space T1, T2, Tn, then a compact set X subset of Cn is said to be a spectral set for this tuple if the joint spectrum. So the joint spectrum for an arbitrary tuple of bounded operators is something that that is a very complicated concept. Its definition is complicated, but whenever they are matrices, meaning they are finite dimensional operators, it's just the joint eigenvalues, nothing else. So the Taylor spectrum of the Taylor joint spectrum of the tuple is a subset of X, and the von Neumann's inequality hold, as I said. Once again, the meaning and everything are same. Okay. And what is a boundary? A boundary is something. It's not only topological boundary. A boundary for this algebra of rational functions is a closed subset delta of X, such that every function in Rx attains its maximum modulus on delta. What is Rx here? It's all complex valued rational functions that of this form P by Q, where Q does not have any zero inside X. Okay, I'm not calling it pole because the word pole is dangerous here. If we talk about a polynomial in several variable P and another polynomial in several variable Q, then P by Q is something. The zero set of Q is not discrete; it's a variety. We will come into that. So better to say, it contains all rational functions of this form P upon Q, for which Q does not have any zero inside X. Now it is called, a closed subset delta of X is called a boundary for this algebra if every member, meaning every rational functions, attains its maximum modulus on delta. And the smallest among all the boundaries, which is the intersection of all boundaries, is called the distinguished boundary of X, and it is denoted by Bx. So that is what I was telling. If you talk about the bi-disk, this 2 torus is the distinguished boundary, and this is the topological boundary. If you look at the definition of boundary, this topological boundary is also a boundary because of the maximum principle. And here we have something that is much thinner. It has a complex dimension 1 and it has complex dimension 0, meaning dimension as a complex manifold. So yeah, and now formally we define what is rational dilation. We are talking in informal language. So if you have a commuting tuple of operators T1, T2, Tn acting on a Hilbert space H, and that has X as a spectral set, then it is said to have a rational dilation or a normal Bx dilation. This Bx is the distinguished boundary. Again, it's dilating to the distinguished boundary in more than one variable. In one variable, all these things will coincide. If you have a nice domain like unit disk, if there exists a bigger Hilbert space and a couple of commuting normal operators n1, n2, nn on K, such that you have this realization once again. You can realize f of t, where f is a rational function, as a compression of f of n. Okay. Moreover, this dilation is called minimal, provided this underlying compact set is polynomially convex. Otherwise, this does not hold. It is called minimal if you can get back K as a span closure of this. Tn acting on H, where H comes from the basic Hilbert space that we started with. Okay. Okay, I skip for now all these things. Now let us come to today's topic. What I wanted to, my work. So I talked about something called spectral interpolation, a family of domains associated with spectral interpolation. So what is a spectral interpolation? This is a simple old question, and it has been an open problem till date. Given k distinct points z1, z2, zk in the unit disk of the complex plane and k matrices a1, a2, ak in the spectral unit ball of MNC, you can choose any n here, does not matter. Okay, this MNC is the space of all n by n complex matrices. So given k distinct points and k matrices, not necessarily distinct, in the unit ball of MNC, whether or not we can find out an analytic function from the unit disk to the unit ball of MNC that will interpolate this data, meaning f of zi will be ai for I equal to 1 to k. So this question remains unresolved till date. If we choose the right hand side, here we have chosen the right hand side to be the spectral, to be the unit ball, to be the norm unit ball of MNC. Instead, if you choose the unit disk on the right hand side also, if you choose k distinct points from the unit disk and another k points from the unit disk itself, then it is called the classical interpolation problem, which is resolved. And one can find out an analytic interpolant if and only if there is something called a pig matrix. That pig matrix is positive definite. But here, if you choose this multivariable setup, meaning if you choose MNC on the right hand side, then this problem is still an open problem. Now, the symmetrized n-disk or the symmetrized polydisk is a domain that is closely associated with the spectral interpolation. How? So it is actually a symmetrization of the points from the polydisk. This Dn is the polydisk, the Cartesian product of n copies of D. And what is the symmetrization map? This is precisely given here. So the symmetrization map, what does it do? It does symmetrize. So given 2 points, say Z1 and Z2 from the unit disk, then their symmetrization is, we call pi2 of Z1, Z2. This is precisely Z1 plus Z2 and Z1, Z2. Now, if you choose 3 points, then it's a map from C3 to C3, actually. And Z1, Z2, Z3 will map to first their individual sum, and then their sum taking product 2 at a time. And then their product. Now you understand what happens if we choose pi4. So the symmetrized polydisk, what we denoted by Gn, is symmetrization of the unit disk, the n disk, and why and how this is closely associated with spectral interpolation. It's given at the bottom. So if a matrix in MNC has spectral radius 1, then the symmetrization of its eigenvalues belongs to Gn and vice versa. So this is how the spectral unit ball of MNC is being characterized by this domain Gn. The spectral radius of a matrix is less than 1 if and only if symmetrization of its eigenvalues belongs to Gn. Okay. And the closure of Gn is something that we denote by gamma n. It's nothing, it's the symmetrization of the closed polydisk, the closed n disk. Okay. Yeah, just for the convenience, I have written down G2 and G3. Now, you can easily notice that if you just look at G2, this is nothing but trace of matrix and determinant of 2 by 2 matrix. It's a collection of these two. It's Z1 plus Z2 comma Z1 Z2. Okay. And as I said, you just look at the above line. It's a symmetrization of the eigenvalues. And what are the eigenvalues of? No, it's not M2C. It's a typo. Norm of A is or spectral radius of A is less than 1. That is something that needed to be mentioned. It's a typo. And the distinguished boundary of this symmetrized polydis, which is denoted by B gamma n, is the symmetrization of the points of the torus. It goes without saying. It's needless to mention that an object like Gn is much easier to deal with than an object like this B1n. If we talk about the spectral unit ball of MNC, so this is an object that is norm unbounded. It consists of all matrices that have spectral radius less than 1, but it's norm unbounded. But an object like the symmetrized polydis that has complex dimension n, it's an open subset of Cn. So it's much easier to deal with. And we have this relation. We have this if and only if relation. Spectral radius is less than 1 if and only if the symmetrization of eigenvalues belongs to Gn. So better we choose this object to study than what is so-called the spectral unit ball of MNC. The primary aim was whether or not we can translate this spectral interpolation to an interpolation problem of the symmetrized polydis. Can this problem be transferred to an interpolation problem where this F will act from D to Gn? So that actually was the primary question. Once again, this is also an open problem till date. Many mathematicians have contributed in this zone, and still it's progressing. So here in this talk, we are going to consider a couple of commuting Hilbert space operators, call them H1, H2, Hn minus 1, P, for which this gamma n, the closed symmetrized polydis, is a spectral set. Because we have seen what is a contraction. A contraction is something that has the closed unit disk as a spectral set. Now here we are doing with the symmetrized polydis in multivariable setting. Now, as we have seen, an operator is a unitary if and only if the unit circle is a spectral set for T. So that is the geometric description of all unitaries. Now one can define in an analogous manner a couple of commuting operators, R1, R2, say Rn minus 1, U, is a gamma n unitary, meaning the analogous notion of unitary for this setup if the distinguished boundary B gamma n is a spectral set for this. Once again, it should be a commuting, once again a typo, commuting normal operators. Okay. So if we talk about the definition of rational dilation, and if we go back, so it's nothing but gamma n unitary dilation of a gamma n contraction. Like for the case of a contraction, it is a unitary dilation of a contraction. Okay. Now in multivariable setting, the dilation does not succeed. We have a couple of evidences. For example, it succeeds on D2, the bidisk. If you have a pair of commuting contractions, T1 and T2, then they can be dilated to a pair of commuting unitaries, U1 and U2, on a bigger space. But this is no longer valid if you move from 2 to 3 dimension. It does not happen in 3 dimension. If you take triple of commuting contractions, T1, T2, T3, then not always you can find out U1, U2, U3 that will dilate. No, not always. It's not always. So in 3 variable or in higher dimension, in more than 2 variable, there is no evidence till date where rational dilation succeeds. So it all boils down to, whenever we talk about multivariable operator theory and its dilation, and the dimension is more than 2, we only talk about special classes of operators that dilate. Once again, the goal is to realize the given tuple of operators, a normal tuple, a tuple of normal operators. That is the goal of dilation. Now, now let us come to our machinery. So it's we have proved that given a gamma n contraction, meaning an n tuple for which the symmetrized polydisk closure is a spectral set, if you have a gamma n contraction, then one can find out few operators, n-1 operators in BDP. What is DP? DP is the defect space. If P is a contraction, meaning norm of P is less than or equal to 1, then DP is I minus P star P. And this script DP is the range closure of this DP. So this is what is called the defect operator, the defect operator of P, and this is called the defect space. So one can easily prove that P is a contraction if and only if this DP is positive definite. So here you just look at, if we have a gamma n contraction S1, S2, S n minus 1, comma P, then the last component is a contraction. And one can find out n minus 1 unique operators, F1, F2, F n minus 1 in BDP, such that this operator equation holds for I equal to 1 to n minus 1. This unique operator tuple is called the fundamental operator tuple or the FO tuple of the gamma n contraction. Now, with the help of this machinery, we will characterize a class of operators, a class of gamma n contraction that will dilate to the smallest dilation space. Once again, it's always a credit to find out the smallest one. So if you have a gamma n contraction acting on a Hilbert space H, and if you have the fundamental operator tuples A1, A2, n minus 1 and B1, B2, Bn minus 1 of the given gamma n contraction and its adjoint respectively, and if K is the minimal unitary dilation space of P. So if you talk about one variable dilation, as I said, if you take one contraction, then it dilates to a unitary, and Am I audible? Hello? Yes, I don't know. I was disconnected. I just kept on talking. Anyway, if you have a contraction, then its unitary dilation somewhat looks like this on the minimal space. Now, if we have the symmetrized polydisk setting, then we have found out a necessary and sufficient condition. If the underlying Hilbert space, the dilation space is kept same as one variable periodic, then such a tuple dilates to a gamma n unitary if and only this two operator tuple becomes gamma n minus 1 contraction for every z. So this is a necessary and sufficient condition. And if it happens, then this is the explicit form of these operators which will dilate the given one. This is Ri, and this is the last component. So this is the explicit form, block diagonal matrix form. Yeah. So for n equal to 2, so that work was done with jointly with Deepta Bhattacharya and Subrata Shamroy, a joint work with these two fellows, and it appeared in Advances in Math 2012 for n equal to 2 case. Now it is generalized. You just look at the conditions, they will follow automatically. It's unconditional for n equal to 2. But in more than 2 variable, it's not unconditional. It's conditional. Yeah. Now the next part is the distinguished varieties. What is a distinguished variety? So if you talk about a pair of commuting contractions T1, T2, then D2 closure is a spectral set. If you talk about a pair of commuting contractions T1, T2, then this D2 closure is a spectral set for T1, T2. Now, recently in 2005, G. Maglar and John McCarthy, they have invented something that was once again path-breaking. So if T1 and T2 are matrices, commuting matrices, meaning they are acting on finite dimensional Hilbert spaces, then one can find out a one-dimensional variety inside D2. So this D2 is something that has complex dimension 2 as a complex manifold. Now one can find out a variety V such that V intersects D2, and when it exits the bidisk, it exits through its distinguished boundary, meaning the two torus. When T1 and T2 are commuting matrices, then they have this variety as a spectral set. So this is what is called the distinguished variety. Now, in this setting, what we are talking about, in this setting, in general, here we have found out an interplay between rational dilation and distinguished varieties. It states that if you have a rational dilation on the minimal space, then it is equivalent to the existence of a distinguished variety. Okay, so there are a lot of other stuffs, but I am running out of time, I guess. So I am showing the last slide. It states the following: if a gamma n contraction has dilation on the minimal space, as I said, with this necessary and sufficient condition, then this is equivalent to the existence of distinguished varieties, two distinguished varieties in the symmetrized polydisk. Once again, if you talk about the symmetrized polydisk, it has complex dimension n, and yet its distinguished varieties are all one-dimensional. Anyway, I'm not going to move any further. I just stop here, and otherwise it's just complicated and technical. So rather, I would like to have questions if you have. So I stop here.
Since there is no question, so let us thanks.
I have a question. This is Suparna here.
Suparna.
Yes. So the thing is, in the beginning also you were instead of the spectrum, you were assuming spectral set, right?
Yes.
And like sort of, and also when you go to the multidimensional setup, you're also assuming this distinguished boundary instead of the topological boundary, right?
Yes.
So is some sort of thinness playing a role in this?
Yes.
Uh,
Yes,
so I
indeed.
mean, is there a connection between the two?
Yeah, it is. If you talk about well, once again I share the screen.
Huh?
Yeah, if you talk about the unit disk, okay, then if you go through the definition of distinguished boundary or topological boundary or anything, they will all coincide here for the unit disk, and it is the unit circle. But if you move from 1 to 2 variable, for example, if you take D2, then its topological boundary is something that has complex dimension 1. It's big. And the
Right.
2 torus is the distinguished boundary. And what is a distinguished boundary? This is something so that all rational functions, complex valued rational functions from D2 closure to C that does not have, P upon Q, where Q does not have any zero here in D2 closure. We are collecting all such rational functions, and this T2 is something, the 2 torus is something, all such rational functions will attain their maximum modulus there. And this is the thinnest, this is the smallest among all closed sets, which are subsets of D2 closure, for which this happens. Okay. So this is the minimal algebra, and we work with the minimal algebra. Yeah, definitely it has got a lot of implications in von Neumann algebraic setting and in sister algebraic setting.
Okay.
Yeah. But we choose the thinnest one, yes.
Okay. Yeah. Thank you so much.
Is there any question? I think there is. So since there is no question, let us thanks to Saurabh Pal for his nice lecture.
Okay.
Thank you, Saurabh, for your nice and informative talk.
Yeah, it's pleasure. It's pleasure of mine. Thank you very much.
Thank you. So one announcement for the participants is that there is a directory session. So at 5:20. So after a parallel session, paper presentation parallel session, please join at 5:20 in this link. Okay, we'll send you a mail again. So just for valedictory session at 5:20, please join in this link. Okay. So thank you. Now we'll meet at 3 in the parallel session of paper bench. Thank you all.